I'm not sure why it does the top thing, but can everyone see it fine still? If not, you can skip forward. But we'll be going over the final exam review. The final exam covers all of what we've learned in Math 1050, but it focuses on half of it will focus on what you've learned more recently. Which is the matrices and the partial fraction decomposition and the solving linear equations and nonlinear equations. Just as a review, in units 1 through 4, in unit 1 was complex numbers, solving equations, functions, graphs of functions and notations. Unit 2 was circles, transformations of functions, combining functions and inverse functions. Unit 3 was quadratics, polynomials in the graphs, polynomial divisions, real zeros, the fundamental theorem of algebra, rational functions in the graphs, and CB4 was the rational inequalities, exponential functions, logarithmic functions and properties, exponentials, and their models. So we'll be focusing first on this most recent unit, and then we'll go into this kind of review. And yeah, this is the most recent, which is matrices and systems of equations, nonlinear systems of equations, partial fractions, and matrix arithmetic. We'll start on matrices and systems of equations. Feel free to stop me whenever if you have a question and we can go over it. So for this first problem, we have a system of equations, and we can use any technique to determine the solution of the following system. So there are a couple ways we could solve this. We could use elimination, we could use substitution, we could put it in a matrix and solve for the row echelon form or the reduced row echelon form. One thing I noticed here is that we have a term positive 5y. Let's see if I can get this. Positive 5y, and we have a negative 5y in the other equation. So we can add the two equations. So if we add these two, then we can get 2x, and then 5y minus 5y equals 0, and then equals 6. So this implies 2x equals 6, which means x equals 3. Then we can plug x equals 3 into either of these equations. I'll do the bottom one. So we have 5 times by 3, which is our x, minus 5y equals 1. So our negative 5y equals, and if we said, I guess it's 15 minus 5y equals 1. You can subtract 15 from both sides. So we get negative 5y equals negative 14. And we get the y, we divided by the negative 5 on both sides, equals 14 fifths. So our point of the solution, it would be 3 14 fifths. And we can see that there. If on the final there isn't this nice, easy, like you can add the equations up, you can multiply equations and then add them up. So like say if this was a 10, then you can multiply the other one by 2 to get the 10y. Or you can always solve for y. So an example of this, if we were solving for y, we would do 5y and move the 3 over, equals 5 plus 3x. And then y, if we divide both sides by 5, equals 5 plus 3x over 5. And then we can substitute that into our other equation. So we'd have something like 5x minus 5 plus 3x divided by 5 equals 1. We solve for x, and then we plug it back into y. So that's an alternative way to solve it when things aren't as nice as that. So, any questions with that? Okay.
Okay. So matrices are another way to solve systems of equations, just like that last problem. They're especially easier when you have more than two equations, because either elimination sometimes isn't possible and plugging in variables is just going to be more difficult. And so we use something called the reduced row echelon form often. And so if we take an example like this, then you have on the left side here is the equations. And so the original matrix, if you were to put this into a matrix, you'd have 5, 4, 3, 4. And so that comes from the first equation. The first column are the x values. Second column are the y values. Third column's the z values. Then the fourth column is what it's equal to. So if we were to keep going down, you got 2, 1, 5, 6, 4, 3, 2, 3. So that's what the matrix, if you were to put those equations into a matrix, that's what it would look like. And then you do some arithmetic within that matrix, and then it provides this reduced row echelon form here. On the test, and so like that arithmetic is like adding the rows together. You multiply rows by constants, and it'll help you eliminate down. On the test, they will give you just this reduced row echelon form. So they'll show you what the equations are, kind of like this, but then they'll give you this, and you just have to determine whether it is independent, dependent, or inconsistent, and then kind of some values that we'll show you right after this slide. So independent, what that means is that for every variable, there's only one answer. And so in this case, what we have, as we know, this first column is for x's, seconds, y's, thirds, or z's. And so if we were to rewrite this, then we would say that this first equation is saying that x equals 1, y equals -1, and then the last one is saying that z equals 1. And so this one would be independent because every single variable only has one answer, and it's not dependent on any. No matter what numbers the other variables are, those aren't going to change. So like if the z value got changed to 3, it wouldn't affect what y or x is. And so anytime you have a matrix that looks somewhat like this with a 1 in each of these, and all these are 0, you're going to know that that is independent. And when you write them out, this can help as well. And that kind of goes into, so this is independent. And then the second part on the test for these problems is to solve for what x, y, and z are. And so that's what I just did on the last one, where this first equation is saying that x equals 1, y equals -1, and z equals 1. Because remember, the first column's x values, y, z, and then it equals whatever is in the last one. Any questions on that? And then there are examples of the inconsistent and dependent ones just right after this. So, okay. So x equals 1, y equals -1, and z equals 1. So here's another example of one that they might give you. And so you have what? You have the 1, 0, 5, 0, 0, 1, -1, 0, and 0, 0, 0, 1. If we were to write this out, then this first equation is saying that x plus 5z equals 0, y minus z equals 0, and 0 equals 1. 0 cannot equal 1, and so therefore this one is inconsistent. It's basically what that means is that there wouldn't actually ever be a solution to this equation. And that might be because two planes are like parallel, something like that. And so this one is inconsistent. If you ever get one of these that says 0 equals 1, is inconsistent because that just is a false statement. And then the last example is this one. So if we were to write out what this matrix is telling us, we have x plus z equals 1, y minus 5z equals 2, and 0 equals 0. 0 equals 0 is a true statement, so it's not inconsistent, but it doesn't help us at all in solving. And so we only have two helpful equations, but there's three variables. And so you wouldn't be able to just solve for what x is based. It wouldn't be like a single number. But what we can do is we can set z equal to z. And then we can solve all the others in terms of z. And so if on any of the quizzes or on this test, if you get one that says 0 equals 0 on the bottom, you get a whole row of zeros, then it is a dependent one because you're going to have to solve it in terms of another variable. And this would happen kind of like if you had two lines on top of each other, then there's going to be like an infinite amount of solutions. And so you'd have to know some like x value, some y value, or some z value to estimate what the others are. And so if we're solving for what x, y, and z are, you got x minus z equals 1 and y minus 5z equals 2. If we just set z equal to z, then we can solve x for x and y in terms of z. So there will still be a z in the equation, but basically in real life what you would do is you would choose some z value that you're analyzing, and then you would plug it in and find what your x or y value was. So if we solve for x, x would equal 1 plus z, because we add the z over from here, and y would equal 2 plus 5z, because you add the 5z. Oh, I just realized a mistake I made. This up here should be x plus z. So it's actually down here, this would be 1 minus z, because you're subtracting the z over instead of adding it. So you get your solutions. You got x equals 1 minus z, y equals 2 plus 5z, and z equals z. Any of you have questions on kind of solving these three different types? On the test, they'll give you, there are two problems that are like this. And so they might both be independent, they might both be dependent, inconsistent, or they might be a mixture. But the test will give you this. And then you just have to solve from there. Okay. That's good.
Okay, so now we'll go over nonlinear systems of equations. So notice how it's nonlinear because there's square terms. So this would be a circle, and this one would be it would also, I guess it'd be an ellipse probably. Right. They're both nonlinear.
Oh, the second one would be an ellipse.
Yeah, probably an ellipse. So they're both nonlinear. And so what we're trying to solve for the same thing where the two lines pass, the two equations are equal. And so what we want to do is we want to find a variable in one, we want to find a term in one equation that we can substitute into the other equation. So notice how both have x squared. So we can solve for x squared on one of these equations. So I'll solve for x squared on the top equation. So x squared plus y squared equals 25. I can subtract y squared from both sides. And I get that x squared is equal to 25 minus y squared. So now that I have a term for x squared, I'm going to plug it in to the other equation. So from this other equation, I have the x squared is equal to 25 minus y squared plus y squared plus 4y equals 13. Now we can add the terms together. Negative y squared plus y squared equals 0. So then we're left with 25 plus 4y equals 13. With this, we can solve for y. So we can subtract both sides by 25. So we get 4y is equal to negative 12. And we can get y is equal to negative 3. Now that we have our value for y, we can plug it back in and solve for x. So I'll use the top equation. It's got less terms in it. So we have x squared plus y, which is our negative 3, squared, equals 25. So we have x squared plus 9 equals 25. And then x squared, if we subtract both sides by 9, equals 16. We can take the square root of both sides, and that means that x is equal to plus or minus 4. So, because x is plus or minus 4, that means we have 2 points where these graphs, the functions cross. So, one of these would be our positive 4, negative 3, and the other would be our negative 4, negative 3. And there's that solution. One thing to note on this equation specifically, because both terms do have an x plus y and an x plus y, you could substitute 25 directly into there and just solve from there. Not all nonlinear systems of equations are going to have that. But just find something in the equation that you can plug into the other equation. Any questions with that? Okay.
Okay. Partial fraction decomposition. This one, in my opinion, might be the hardest of all the new stuff. But once you understand it, it's not too bad. And it is especially helpful if you go on to calculus or other math classes. So setting them up, things to keep in mind. So on the top one we have, for each linear factor, we need a fraction with a constant on top. So let's say you had some equation, and in the bottom, you had like an x plus 1 and an x minus 1. If you were trying to decompose this, you would have some a over x plus 1 plus some b over an x minus 1. Whatever your factors in the denominator are, you want to break them up. And then the second part says for each quadratic factor we need a fraction with a linear equation on top. I think what this is saying is if you can't factor what's in the denominator, then you can keep it like this, but then you'll have to have an ax plus b in the numerator. But that would only really be if you can't factor the denominator, otherwise you will want to separate them out. And then the last one is also super important, where it says if you have any squared or higher powered factors, you need another term. So let's say if you had something over an x plus 1, and let's say you had like an x minus 3 squared, then you not only would have an a over x plus 1, you'd also have a b over an x minus 3, and a c over an x minus 3 squared. That's another important one to keep in mind. And when you're solving them, what you want to do is you want to get a common denominator. And so you'll leave the a, b, and c's in there. Those are some constants that you'll end up solving for. And so you find a common denominator, you group together the terms, And so any x's, you're going to group those together. So if it's like an ax plus bx, you'd group those together. And then you set it equal to the original fraction. Then you set up system of equations and solve for the variables. And I'm sure that's just a lot of words right now, but as we get into an example, it'll make sense. So, write the following fraction or rational expression as a sum of partial fractions. So I'm going to start by factoring the denominator. So this is equivalent to a 4x plus 16 over, this is an x plus 1, x plus 5. And so if we expand that out to our partial fractions, we're going to have an a over an x plus 1 and a b over an x plus 5. And we don't know what a and b are, and so that's what we're solving for here. So the next step would be to find a common denominator with those, and then to add them together. So if we try and get these to be a common denominator, we need an a times by an x plus 5, which will be over x plus 1, x plus 5. And then you'd add that to a b times by an x plus 1, all over that. So now I'm going to expand this out and put them all in the same fraction. So if we do this, you have an ax plus 5a. You also have a bx plus b. And that's all over the same x plus 1, x plus 5. And we want this to be equal to the 4x plus 16 over an x plus 1, x plus 5. If we look at those two fractions, you can see that the two denominators are equal to each other. And because of that, we can therefore just set the two numerators equal to each other. And so ax plus 5a plus bx plus b has to equal 4x plus 16. Now we want to group together like terms. So anything on the left-hand side of the equation that has an x, we're going to group together. Anything that doesn't have an x, we're going to group together. And so we have an ax plus bx plus 5a plus b, those are kind of grouped together, equals 4x plus 16. The terms that have an x in it, we can factor out an x. So then you get an a plus b times by x plus 5a plus b. All right. So now to get our system of equations to solve for, we have these two sides are equal to each other. You see that the left-hand side has an a plus b times x, and the right-hand side has a 4 times x. There's never going to be an x that goes in with the 5a plus b, and so the terms that have x are going to be set to equal to each other. And so a plus b is going to have to equal 4, because a plus bx equals 4x. And then the same with the other terms, 5a plus b equals 16, because those don't have any x term associated with it. Now we have this system of equations, so we can solve them just like we did before. where you can either use elimination or you can use substitution. And so in this case, what I'm going to do is I'll just solve the first equation for b. And so this is going to be b equals 4 minus a. And if I plug that into the second equation, then I get 5a plus 4 minus a equals 16. So that is 4a plus 4 equals 16. 4a equals 12. And so a equals 3. Now if I plug that back into either of the equations, I'll just plug it back into my b equals 4 minus a. B equals 4 minus 3, which equals 1. So then, now that you've solved for a and b, you just need to substitute those back into your regional equation up here to this one. So our answer, I'll write it at the top here. A we have is 3. 3 over an x plus 1. And b we have as 1. And so if we check the answer, that says 1 over x plus 5 plus 3 over x plus 1, which is what we have at the top there. So that is the basics of partial fraction decomposition. There are definitely a lot harder ones on the test. And so at the end of the review, we could go over a more difficult one. Because this one, you'll have two problems on the test that are partial fraction decomposition. One will be similar to this, and then the other one you have to use polynomial long division before you do the decomposition. And also if there are terms in the denominator that are squared, it'll be more complicated. So at the end we can go over one that's more difficult.
Okay, now we'll go over matrix arithmetic. Matrix addition and subtraction, so you have each place in the matrix, and when you add matrices together, it has to be the same size matrix in order to add them together. And you, as you can see, it's A plus E, so you take the one in this position and add it, and then the same B plus F, and so on, C plus G and D plus H. So you just add each term position together. With scalar multiplication, you have the scalar right here, and it multiplies to each position. So k times A, k times B, k times C, k times D. And then with matrix multiplication, this one's a little weird, but you multiply this row by the first column for this. So you A times E plus B times G. Then for this position, you multiply this row by this column. So A times F plus B times H. Then down below it's C times E plus D times G. And then finally the last one would be C times F, D times H. So you kind of like go the row by each column, and then down one you go row by each column. And then you multiply the term and add them together. So we'll go over an example, but that's kind of what you do. So this one is multiplying matrices. One thing to note is that you can't multiply every matrix. So we have a 2 row by 2 column matrix here, and then the same 2 by 2. These middle ones, if you're multiplying together, need to be the same. Otherwise, you can't multiply the matrix. And the resulting matrix will be the edge. So we'll get a 2 by 2 matrix as a result of this multiplication. So if we set up our matrix, we're going to multiply this row by this column. So we're going to 4 times 10, and then we're going to add that to our negative 2 times negative 9. Now for this next corner, we're going to do this row by this column. So we're going to do 4 times 4, and then we're going to do -2 times -10. Now we're going to go down a row, now that we've done all the columns. So now we'll be focusing on this row. So we're going to do -9, and then first column, so -9 times by 10. So we have -9 times by 10, and then we're going to have our 2 times our -9. And then we'll go next column, so -9 times -4, or sorry, times +4, plus 2 times -10. So if we simplify that, we'll have 40 plus 18 here. This one will get 16 plus 20. We'll get -90 minus 18 here, and we'll get -36 minus 30 here. And finally, our finished matrix will be, what was that?
It's -20.
Minus
It's
20.
2 times -10.
Oh yeah, sorry. -10. So let me fix that. So yeah, and then back to this. Plus 20. Minus 20. That's -9. Okay, sorry. Okay, so we got 58. We had 36 here. We get -108 here, and we get -56. Great. Okay, thanks. As we can see there. So, any questions with matrix multiplication? Okay.
Okay. In my opinion, matrix addition is quite a bit easier than matrix multiplication because you don't have to deal with so much multiplying and adding and keeping track of terms. Because like was said before, when you're adding together, you add basically the same position. So if it's in the top left, you add it to the top left. But to make things easier first, we have these constants out in front. So we have that -1 there and that 2 there. And so I'm going to multiply those into the matrix. And so if we do that, we end up with a 2, -5, -3, -5, added 2, -6, 0, 10, and 6. So now that we don't have any constants out in front, we can do the addition. And so you have a 2 minus 6. You got a -5 plus 0, -3 plus 10, -5 plus 6. So if we were to simplify that, 2 minus 6 is -4. -5 plus 0 is -5. -3 plus 10 is 7. And then -5 plus 6 is 1. And that should be the solution. Any questions on adding or doing operations on matrices? Okay. Then functions.
Okay, to start off with functions, we're going to go work on this problem, which is a quadratic. So here we have listed off the steps. So we want to identify the parent graph. Now usually quadratics come, in some form of ax squared plus bx plus c. However, when we're given the vertex and given other points, we can use a different form of the quadratic, which is our y equals a x minus h squared plus k, where our vertex is our HK. So on the graph, we can see our vertex, which is the point, the point where it changes direction, right? It bounces off right here. So our vertex would be our -2, -3. So we know that's our vertex, and our transformations, usually it starts at 0, 0, right? So that's where we base our transformations off of. And we know that it moves to the left by 2, and it moves down by -3, right? So because it's in the parentheses, our x is going to be x plus 2, and our y is going to be y minus 3 is kind of our transformations there. So we know that we have our y is equal to a, and we plug in h and k, which is our -2, x minus -2 squared, and then minus 3. So now that we have our base equation with the vertex plugged in, we can use either of these points, and we can plug in and solve for the unknowns. So I'll use this point right here, the -3, -2. And so you can plug in the -2 for y equals a, and then our x would be -3. Minus the negative is a positive 2 squared, and then we would have minus 3. So if we simplify that, -2a, this will become -1 squared minus 3. If we move the plus 3 on both sides, we get that our 1 is equal to a times by 1. So a is equal to 1. So our final solution is that y is equal to x plus 2 squared minus 3. Yeah.
Is it a pretty high probability on the exam that the A will probably be 1?
I'm not sure, but it's always a good idea to just plug in and check.
Okay.
So it could be 1, it could be a different number, but it's always good.
Okay.
And one thing to note too is if the parabola goes here, then you should expect a -a if it's facing downward.
Yep.
Yep. Any other questions?
I think the common functions that you'll see are either a cubic like this, or not, this is a cube. This is a parabola, a square. You might see a cubic. I know I've seen square roots, and then you might also see a cubic root. I don't know if that one actually comes up, but there's a chance. And so if you see that one, the original graph for a cubic root kind of just looks like this. It's like a square root, but also on the other side. So I don't know if those do come up, but those are the only ones that I would expect to see if there are some. Any other questions on these? Okay. So now, this time they give us an equation. They give us a quadratic, and they say evaluate f of 3 and f of x plus h. So if we kind of look at the notation, the graph, they say f of x equals those. And so what f of 3 means is that you're plugging in 3 for x. So f of 3 equals 3 times by 3 squared minus 4 times by 3 plus 8. So if we expand that out, you got 3 times by 9 minus 12 plus 8. So that's 27 minus 12 plus 8, which equals, so that's 30. So that's negative 12 plus 8 is negative 4. Plus 27 would be 23. And then if you have f of x plus h, then you could plug in x plus h for all your x values. And I believe if you just plug that in, that should work on the test. And that's the answer that they give there. See, in this course, you don't have to expand that out a ton. If you do go on and take calculus, they'll have you expand it out at least once or twice because it'll prove a concept that you'll learn there. Any questions on this? Just whatever is inside those parentheses, that's what you plug in for x. And that's our domain.
Yep. Okay, now we'll go over domain of a function. So it's all the inputs of a function that are real numbers. And it has a real number output as well. So when finding the domain of a function, we usually find what values are not in the domain. So we're looking for what would make the function undefined or what would make it an imaginary number. So 4 things to look at is the piecewise functions. So those ones usually will have they'll say from 0 to x, you'll have this function, and then from 3, x is greater than or equal to 3, you'll have another function. Those are piecewise functions. So they'll have the domain set for each function. And then you have fractions with x in the denominator. So anytime you have 1 over x, x can equal 0, or else it's undefined. Square roots, they can't be negative. So if you have a square root of x, x has to be greater than or equal to 0. And then logarithms with x in them. So they have to be greater than or equal to 0. They can't be less than 0. So for example, log of x, your domain would be x is greater than or equal to 0. These two, they can be combined. For example, sometimes you'll have a 1 over square root of x, which means that x can equal 0 either, and it has to be greater than 0. And in interval notation, this would look something like 0 to infinity, right? So you kind of have to piece them all together and take the most limiting domain.
And remember with logs, it can't equal 0 inside.
Oh, sorry. Yeah.
It has to be greater than 0.
Yep, greater than 0, thanks. So with our interval notation, if it's not included, it's going to have a parenthesis. If it is included, it's going to be a bracket. So, for example, this would be, and if it's anytime an infinity, it's going to be just a parenthesis. So you're going to have negative infinity here, and it's going to go to negative 2. But because it's open circle, it's not going to actually hit negative 2. So you would just have a parenthesis there. Then you use the union sign, so the u. And then our next interval that we're going to is 3. This is included, so I'll have a bracket there. And that will go to infinity. So an example of this we can do is this one. So we have a couple terms here, and each kind of have their own domain. So our first one here, we notice that there's a square root, which means that it has to be greater than or equal to 0. Like the term, I guess. So we'll call the term inside y. Has to be greater than or equal to 0. And it cannot equal 0 because it's in the denominator. So we can set that equal to a 2x plus 8 is greater than 0, because it can equal 0, but it needs to be greater than 0. If we solve that, we get 2x is greater than negative 8. If we subtract 8. And if we divide both by 2, we get x is greater than negative 4. Now for this term, we know that the denominator cannot equal 0. So we can put that 6x minus 5 cannot equal 0. So 6x can equal 5. X cannot equal 5/6. Then our final domain, we have a natural log here, which functions the same as a log, whereas x plus 3 has to be greater than 0. So we know that x in this case has to be greater than 3. Now we can combine them all to find the domain of the function h of x. I like to write a number line to keep where things are straight. So we know that we have a negative 4 here, and we know that it has to be open circle and it has to be greater than negative 4. Then we have over here we have a negative 3. And it's also an open circle and it has to be greater than. And we know that x cannot equal 5/6. So here on the number line it's greater. We have a hole right there. So now we take the most limiting domain. So because we already have an x has to be greater than or equal to negative 3, this section here that's between negative 4 and negative 3 doesn't really matter because it's already included in the domain of another one. So we'll start at negative 3, and it's a open, it's just a parentheses because it's not included. We'll have negative 3, and we'll go until we hit the next hole or limiting function, and so that would be 5/6. It's not included, so that would be also a parenthesis, and then you have the union sign, and then we'll start there again because it's just a hole, and then that goes to infinity. So that will be our domain of that function. Any questions with that? Yeah.
Why didn't you put a negative 4 again?
So because the negative 4 is already, so we have all this included with negative 4, right? Say if we plugged in negative 3.5. So for this first one, it would be okay, right? X is greater than, negative 3.5 is greater than negative 4. But say we plug in negative 3.5 here for x. Is this true? No, right? And so that would not be true. So we can't plug in negative 3.5. So our most limiting domain would be from negative 3 on. Because any x you plug in that's within this range is a real number in our function. Or sorry, any number you plug in that domain is a real number in the function. Any other questions? Yeah.
So how do you know when it's like included or not included?
So we know that we find each place where the domain is limited. So like we have our square root here, and we also have the denominator. It's any of these they limit our domain. And then it's any real number input that has a real number output. So if we go back and do a couple examples, if we plug in negative 5, we're going to run into a problem here. This will be a negative. And this will also be a negative number, which means that it's outside of that function, and we'll get an imaginary number or some other non-realistic number. And so that's kind of where we take it, and then if we plug in negative 3.5, right, it may work for some parts of the equation, but not all the equation. And so we're looking for any x that's within this domain. If we plug it in, it will equal a real number as an output of the function. Does that answer your question?
Yeah.
Good question. So any other questions?
So now combining functions. And so when you combine functions, you might get notation like this listed here, where you have parentheses f plus g of x, which is saying that you have f of x plus g of x. Or you could have division. So if you're doing multiplication, subtraction, or addition, the domains just have to satisfy both functions. But with division, you have to make sure that you're not dividing by 0. But pretty much what you'll do with these is if you have f of x plus g of x, you find what f of x is, and then you add it to what g of x is. And then same with division, except you would do division. And so with an example, I guess here's the domain. So the domain is all those for which f of x and g of x are both defined. So kind of like in the last example, how you had from negative 4 to infinity and negative 3 to infinity. If, let's say, f of x, its domain was from negative 3 to infinity, but g of x was from negative 4 to infinity, the negative 3 to infinity is more specific, and so that would be the domain of the whole function, because it has to satisfy both, just like it did in that example that Sam did. And then with domain, like I said, you just have to make sure if you're dividing whatever's in the denominator, it cannot equal 0. because you can't divide by 0. And then you have composite functions. So if you do f of g of x, then what that means is you find g of x and then you plug that into the function f. So whatever y value you get out from doing that, you plug into your other function. And the domain of it, what you do, it says consistent of all real numbers x such that x is in the domain of g and g of x is in the domain of f. So what that means, because you have f of g of x. And so you plug in some x value and it immediately goes into the g function. So you make sure that it satisfies that. But then the function that goes into f is g of x goes into f. So you have to make sure that whatever output you get from g of x is going to satisfy whatever is in the function f. Okay. So here is a part. Problem 12, part 1. If you have f of x equals 1 over 2x squared plus 1, and g of x equals the square root of x minus 3, find f plus g of 4. So if we found that, then f of 4, that's the same as f of 4 plus g of 4. And f of 4 is 1 over 2 by 4 squared plus 1. And g of 4 is the square root of 4 minus 3. So this is 1 over 2 times by 16 plus 1. And then that is the square root of 1. The square root of 1 is just 1. And we can add this up. So this is 1 over 33 plus 1, which would give us 34 33rds. And then if we do f of g of 6, then this is the same as doing f of g of 6 is the square root 6 minus 3. You can simplify that, f square root of 3. Now if you were to plug square root of 3 into your equation f, then you get 1 over 2 times by the square root of 3 squared plus 1. That's going to equal 1 over 2 times by 3 plus 1, which equals 1/7. And so your answers for this top one, equals 34 33rds. That one equals 1/7. Any questions on how I got those values or in general? Okay. And then the second part of this has to do with finding the domain. In my opinion, this part's the trickier part. And so it says find the domain of f of g of x. So what I like to do is I start off by finding the domain of both just f of x and g of x. So if we have the domain and we have it of f of x, there's nothing that's going to create or have a domain restriction in f of x. The one that we might think of is dividing by 0. But in this case, whatever x value you plug in there is going to get squared, so that value is going to be a positive number. And then you're adding 1 to it, and so there's no instances where you're going to get 0 there. And if you wanted to prove that, you could write down and say 2x squared plus 1 cannot equal 0. And so then 2x squared cannot equal negative 1. X squared cannot equal negative 1/2. So then x cannot equal square root of negative 1/2, plus or minus that. And that's an imaginary number. And so you're never going to put into your function an imaginary number. That was one of the things with domain, is that you're going to put into it some real number. So f of x is all real numbers, so it'd be from negative infinity to infinity. G of x, the domain, we have the square root of an x minus 3. And so we know that what's inside the square root can't be negative. So x minus 3 has to be greater than or equal to 0. In this case, it can equal 0, because you can take the square root of 0. The only time that that wouldn't work is if it's in the denominator. And then that's not the square root limiting it, but the fact that's in the denominator limiting that. So if we solve this, x is greater than or equal to 3. So if we were to write that out, it goes from 3 to infinity. So those are the domains of just the individual functions. So if we want to know the domain of f of g of x, we start off, you have f of g of x. You start off by dealing with the function that's on the inside. So with g of x, you know that the domain restriction has to be from 3 to infinity, just to start off with, because g of x is going into that function. And so then you look at the domain restrictions of f, because that's the outside function. Yes.
Real quick, is the 3 a bracket or a parentheses?
It would be a bracket in this case. Yeah. Because it can be equal to 3. That'll give you 0.
Okay.
So, yep. So we have this. That's the domain of g of x, which is what you're putting into f. And then you look at f, and you're saying, okay, what numbers can I not put into the function f? In this case, though, f of x, you can put anything into it. And so therefore, that doesn't add any additional restrictions onto it. If f of x had restrictions, then you would have to figure out where g of x is equal to those restrictions, and then you would solve for those. And that's when it becomes more complicated, but they won't usually give you 2 of them that'll have restrictions. But let's take an example where let's say f of x had the restriction where it was from like 4 to infinity. I don't know if this is going to work at all or if there will be a restriction at all. But what this is saying, if you were to say f of g of x, then this is saying that x has to be greater than or equal to 4. But x values aren't what's being put into your function there, because if you have f of g of x, then g of x has to be the greater than or equal to 4. And then you could plug in g of x into here. You do square root of x minus 3 is greater than or equal to 4. You could solve that out and figure out what x values would not be in your domain. So that's what would happen if the outside function has domain restrictions. If it's only the inside function that has domain restrictions, like this case, g of x is the only one that does, that's the only one that you have to worry about. Because anything you get will be able to be put into f.
What would the answer to the theoretical one look like?
Theoretical one. So this would be the x minus 3 greater than or equal to 16. So x is greater than or equal to 19. Because if you were to plug a 19 into g of x, then you would get out a 4, which would then not satisfy this. Well, let's see. X is greater than or equal to 19. Yeah, because if you plug anything smaller, am I missing anything on it?
That's right.
That's
it's
right.
A bracket with a 4, so that'd be released.
So then this would basically be your domain restrictions there. The x is greater than or equal to 19. Because the 4 to infinity is already included in the fact that it has to be greater than 19.
Okay, cool.
Yeah. Okay. But in this case, that's It's 3 to infinity. The other one was the theoretical.
Okay, now we'll go over inverse functions. So the definition is that the function f and g are inverses if you plug in g of x to f equals x, and the other way around. If you plug in g of x, if you plug f of x into g and equals x. So this would be written as like if you plug in g of x into the function of x, that would equal x. And if you did the opposite where you plugged in f of x into g, that equals x. We can do that more easily by switching x and y and then solving for y. So in this case, we have it, and we know that f of x is also just y. So y is equal to 5 square root of 2x plus 2 minus 6. And if we switch the x and the y, now our inverse function will be x is equal to 5 square root of 2y plus 2 minus 6. Now we can solve for y for that inverse function. So we can add 6 to both sides. So we know x plus 6 is equal to 5 square root of 2y plus 2. Divide both sides by 5. So we have x plus 6 over 5 equals a square root of 2y plus 2. We can square both sides. And I'm going to come up here. So we had x plus 6 over 5 squared is equal to 2y plus 2. Subtract 2. So we have x plus 6 over 5 squared minus 2 equals 2y. And then finally we can divide both sides by 2. So our y is equal to x plus 6 over 5 squared minus 2 divided by 2. And this one would be our inverse function, which is written as such. So that would be our inverse of the function. X plus 6 divided by 5 squared minus 2 divided by 2. And notice how it kind of looks like the inverse, right? We have a square root term in the first, and the inverse function has a squared term. And so it kind of looks like they would be inverses. Any questions with how to get an inverse function? So the domains and ranges of our inverse, they're going to be the opposite. So the domain of the original function is going to be the range of the inverse function, and the range of the original function is going to be the domain of the inverse. Since most of the time it's easier to find the domain than the range of functions, we can solve for the range of the inverse using the domain of the original, and we can use the domain of the inverse for the domain of the inverse, or the range of the original. But we also need to check and make sure that our original function doesn't impose any restrictions as it is. So we had this, and we know that our function was, if I'm remembering right, x plus 6 divided by 5 squared minus 2 divided by 2. So that's our function, right? And our domain of that function, if we just look at the inverse, would be all real, right? There's no restriction because x is in the numerator. There's nothing that will make that function undefined. There's no square root term. However, if we look at the original function, we notice that it has some translations. And because it's a square root function, we know it comes and does something like this. So there is a range restriction because the range is not all real. And we know that the range here is our y value, our y translation in that. And so we know that it starts at something negative 6 is where our range starts. Our x value is going to be somewhere there. We don't need to know the x value at this moment, but we can know that because it's shifted down 6, that will be where our range starts. So our range of this function would be -6 to infinity. And because of that, our domain of the inverse is going to be the same as the range, so it would be -6 to infinity. Now, to solve for the range of the inverse, it's the same as the domain of the function. So the domain of f of x, that would be our limiting factor there would be the square root. Since it's in the numerator, we know that 2x plus 2 has to be greater than or equal to 0. So we can solve for x there. And we know that x has to be greater than or equal to -1. So the domain of our f of x, which is the range of our inverse, is our -1 to infinity. So the biggest thing here is that if you have the square root function, know that there is a range restriction and that will come in with the domain. If there isn't that range restriction with like a square root, then you can solve for either the range or the domain, and just know that the inverse is just switched. The domain and range are just switched from the original. Any questions with that? Okay.
Okay. Polynomial functions. So graphing polynomials. In order to graph polynomials, we want to find the zeros and their multiplicities and then look at the end behavior. So what the end behavior is pretty much if you go really far on the right hand side, what does the graph look like? If you go really far on the left hand side, what does it look like? You know, is it positive, negative? Does it approach a value? Stuff like that. And so we have this example here. So choose the function from the following whose graph is shown. Assume a, b, c, and d are all positive real numbers. So we have this graph over here. And the first thing that I kind of look at is what is the end behavior. And so if you just were to like ignore all the stuff in the middle, it kind of looks something like that. And a normal cubic function or a normal function that's odd, if it's positive, then it'll look like this. Because a positive cubic function looks like that. If it was negative, then it would be the inverse. And so because this one it opens down on the left and up on the right, we can already eliminate that it's a positive A, so it's not that one, not that one, and not that one. On the test though, there are a really long list of them, so you probably don't want to just eliminate them one by one. And so what you want to do is you'll now go on to the x-intercepts. And so what we found so far is our function equals some positive value a. And then we have 1, 2, and 3 x-intercepts. We have 2 of them that are on the right-hand side of the graph. And so those values are going to be x minus some value. You have 2 of those. And you have 1 that's on the left-hand side, and that's going to be x plus some value. Yes?
Does it matter like where they're placed in it? Like the x minus b, x minus c, x plus d. Can like the d and the c be switched at all, or like?
They could be,
They could
yeah.
Be. Okay.
From what I've noticed on all the tests, like this example doesn't follow that, but from what I've noticed on all the practices that I've done, is I'll start from the right-hand side of the graph and go to the left-hand side. And so they'll always start with like the x minuses and then go to the x pluses.
Okay.
But it wouldn't actually matter because you don't know what B, C, or D is, so it could be swapped.
Okay.
Any other questions? Okay. So now that we know how many x-intercepts they are and kind of which side of the graph they're on, now we look at the multiplicities. And so if we look at this far one over here, you see that that bounces off the graph, which means it kind of looks like a quadratic right around there. So it would be a square, multiplicity of 2. And then the next one over kind of looks linear through there. It just passes through it. So that's a multiplicity 1. And then on this side, once again, it bounces off the graph. And so that one's a multiplicity 2.
Does for x minus b and x minus c, can the square root of 2 be on either one of them, or does it have to be on x minus b?
It could be on either one of them, because once again, we don't know what b or c is. So yeah, as long as you have one of them that's on the x minus b or the x minus c. Yep. Okay, so now that we have that, now we can kind of look through these and see which ones look the closest. So this first one, you can see it says an a, x minus b squared, which looks similar, but then they have an x plus c and an x plus d squared. So what that's saying is that you have 2 of your intercepts are going to be on the negative side of the graph, which is not what this graph has. And so this one here is what our graph has, because it says that you have one intercept that the x plus b will be on the negative side of your graph, the left-hand side. And then 2 of them are going to be on the right-hand side because you have x minus c and x minus d. And then just like we have down here, one of them that is the x minus has the squared, and one of them that's the x plus has the squared. Any questions? Okay. Sweet. T of x.
Okay, now we'll talk about graphing rational functions. So these will have some sort of, this function looks like x plus b, some term up here, x plus c. If you factor it out, x plus d, x plus e. So some sort of polynomial that's gonna kind of have a form like this, and that's what we're gonna be looking at. So wholes are any term when you have, like, say if we had another x plus d term up here, because they're same factors on the numerator and the denominator, those would divide to 1, but there is a hole in the graph there. So it would look kind of something like you go to this point, have a hole, and then keep going. And so that's any place where there's a factor in the numerator and the denominator that is equal. The way you find that hole is so your hole would be at x equals negative d, and then you plug negative d into the reduced form, which is what's left after you divide the hole out. That would be your y value, is what you plug your x, when you plug the x into that equation. So that's holes. Our vertical asymptotes are whatever's left in the denominator. That's where that cannot equals, it is undefined, right? So we know that if we plug in e, a negative e, for example, because x plus e is a factor in the denominator, x plus e, equals 0. So your x is equal to negative e. Then if you plug that negative e in, it would be a 0. The function would be undefined. So what you get there is a vertical asymptote. And that function usually it approaches that on either side. The zeros, you focus only on the numerator. And so going back to this, you have x plus b is a factor. So you know that x is equal to negative b. And you have x plus c is a factor, so you know that x is equal to negative c. And so those would be your zeros. So you only focus on the numerator when you're looking at the zeros. For n behavior again, that is more of your x values of where that x is going. the end behavior is a horizontal asymptote if the degree in the numerator is bigger than the denominator. So if you have 1 over x, for example, the horizontal asymptote would be at x equals 0. Even if you had like x squared over x cubed, your horizontal asymptote would still, it would be at y equals 0. Where is it? There we go. So you have anytime the denominator is bigger. If the degree in the numerator is equal, so say something like we have ax squared plus bx over here, and then we have like cx squared plus a constant e. If they're equal, what we get is we have a horizontal asymptote at whatever their coefficients are of the highest, of the x with the highest degree. So we have a over c in this case. Whatever else is in that function doesn't matter. It's just the coefficients of the highest x, with the x with the highest exponential. So you divide those coefficients for that. And then it's an oblique or slant asymptote if the degree in the numerator is exactly 1 greater than the degree in the denominator. So example of this would be ax, we'll do cubed over bx squared. So that would be a slant asymptote. And you have to do polynomial division. So you would put the bx squared in here with the ax cubed. And then whatever else is in that too, you would do. And that would be an asymptote that would go something like this. So it would be slanted or oblique. So an example of this is this problem. So first of all, we're going to go vertical asymptotes. So if we factor out the bottom, we have our function f of x. Our top is 2x plus 5, and our bottom is a difference of squares. So we know that the factors are x plus 2 and x minus 2. Now first we look at any holes. Because there are no factors in the numerator that are the same in the denominator, this graph has no holes. So now for vertical asymptotes, we look at the denominator, right? And wherever the denominator is equal to 0, that's where we have a vertical asymptote because the function is undefined there. So we have two places where if we plug in an x value, the denominator could equal 0. That's at x plus 2 is equal to 0. So if x is equal to negative 2, and we have if x minus 2 is equal to 0, which is x is equal to positive 2. So we have a vertical asymptote at x equals negative 2 and a vertical asymptote at x equals 2. Any questions so far? Okay. Now we can look for horizontal asymptotes. So notice how the degree in the numerator is a 1, which is our exponent of the highest, the exponent of the x, the highest exponent of the x term. And our degree in the bottom is a 2. Because the denominator has a bigger degree than the numerator, we know that our horizontal asymptote will be at 0. Again, look at the degrees, and then that will determine where your end behavior is. And then now we'll look for where the graph crosses the x-axis, also called zeros or x-intercepts. And that will be focusing on our numerator only. So we have 2x plus 5 equals 0. So we have the next intercept if we have an asymptote at 0.
You have to solve for it.
Okay, so we have 2x equals negative 5, x negative 5 halves. Yep. And that would be at negative 5 halves, 0, because that's where y equals 0. So yeah. So you have that, and then you have your vertical asymptotes, your horizontal asymptote, and your zeros, and then you can start plotting a function. Any questions with that?
Okay. And I believe this is the final section that is on the test, is on logarithms and exponents. And so you'll be given some equation like this, where you have 2 times ln of x plus ln 10 equals 3. And so you're trying to solve for x. So there's multiple ways to do this, but the easiest way, in my opinion, is to try and get everything that's in the natural logs together. So there are a lot of properties that logs have. One of them is, well, you'll see 2 of them here, where you have, if you have a constant multiplied by a natural log, you can raise whatever is inside the log to that power. So what that means is that this ln, or this 2 times ln of x, will become ln x squared. And you still have the ln natural log of 10, and that equals 3. And then another property is that if you're adding logs together, that means you can multiply what's inside those logs together. And so this would then become the natural log of 10 times by x squared, because you're adding them together, equals 3. If you're subtracting them, then what that would mean is that you would do whatever log you're subtracting, that would go in the denominator. So if this were like an ln natural log of x squared minus natural log of 10, then that would be the same as an x squared divided by 10. So if you subtract them, you're doing the division. If you're adding them, you're doing multiplication inside your log. So now to undo a log function, you raise it to the power of whatever the base is. So natural log is log base e. And so on this side, we're going to do e to that power and e to the power of 3 there. And so the e and the natural log will cancel out. And you get 10x squared equals e cubed. Now if we solve for x from here, then x squared equals e cubed divided by 10. Then x would equal plus or minus square root of e cubed over 10. But then you would check to see if it is really plus or minus because of the domain. And you could see if you were to plug in a negative into your original function, then ln of some negative number doesn't exist. So your actual answer would just be that x equals square root of e cubed divided by 10. And then you can plug that into your calculator and get a decimal approximation, which is 1.4172. So that's all for those problems. So if you do need more help, you can go online and watch past YouTube videos, or the tutoring center will be open next week on Monday and Tuesday, and then Wednesday in the morning and after 2, from like 2 to 6. So I think it's in the morning till about 11:30, and then they'll be open as well from 2 to 6, but they'll be closed on Thursday and Friday as well. So that's all that is prepared for this. Would anyone want me to go over the more complicated partial fraction decomposition? Okay, let's see if there's slide. Empty slide. All right. So this was one that I pulled from one of the practice tests. And so the equation they give you is a negative 5x to the x. Come on, let me write. It's negative 5x to the 4th. Fine, I wrote it too high up there. Negative 5x to the 4th plus 15x cubed minus 6x squared minus 14x plus 8 all over x cubed minus 2x squared. So the way that you'll know whether you have to do polynomial division first is if the degree of the numerator is greater than or equal to the highest degree in the denominator. So in this case, our highest degree term is x to the fourth, while in the denominator it's x cubed. And so because it's higher in the numerator than the denominator, we have to do long division first. And then partial fraction decomposition after that. So if we do that, then when we do our long division, x cubed minus 2x squared divided by negative 5x to the fourth plus 15x cubed minus 6x squared, 14x plus 8. So negative 5x to the fourth is going to go into x cubed negative 5x times. And so then when we multiply that out, negative 5x to the fourth plus 10x cubed, and you subtract that whole thing, and you're left with 5x cubed. Make sure I'm doing this right as I go along. Minus 6x squared. I'm just pulling down that negative 6x squared. And then I'll just pull down everything actually. So now if I do this again, then I would add a 5, because 5x cubed goes into x cubed 5 times. Or if you were to divide them, that's what you would get. So then 5x cubed minus 10x squared. Subtract off that whole term, and you get 4x squared minus 14x plus 8. And that's the remainder that you would end up getting. And so this whole thing, once you're done, 4x squared minus 14x plus 8 all over an x cubed minus 2x squared. So when you do your long division, that is what you end up with. Any questions on the long division part? Okay. I'm going to write this up in the corner so I can give myself some more space. So that's what you get from the long division. Am I good to erase my long division work, or are people still writing it down? Okay. If you do need it later, you can either go onto the YouTube channel and watch it, or talk to me after and I can show you my work. All right, so that's the first step to this problem. Next is the partial fraction decomposition part. And so the negative 5x plus 5, you don't have to decompose any further because that's already pretty simple. But then it's the 4x squared minus 14x plus 8 over x cubed minus 2x squared that you'll want to do your decomposition with. So if I were to rewrite that denominator, another way to write that, you have 4x squared minus 14x plus 8, and the denominator factors to an x squared and an x minus 2. Remember, with partial fraction decomposition, you'll want to factor the denominator so that you know what to decompose it into.
Would you want to go one step further and make it x times x minus 2, or is x squared good enough?
X squared is good enough, and I'll show you why in the next step. Because when you have a squared term, one of the rules earlier on that we went over is that you'd have an a over whatever the term is squared, you'll just have 1 of it. And then you'll also have a b over whatever that term is squared. So that's kind of how you account for that. And then you also have the c over x minus 2. So now we want to get a common denominator here. And so you have an a. The a needs to be multiplied by an x and an x minus 2 so that it'll all be over an x squared times an x minus 2. And the b needs to be multiplied by an x minus 2. And the c will need to be multiplied by an x squared. So now if we combine those together, then this a, so the x times, I'm going to write this to the side, x times by an x minus 2 is x squared minus 2x. So if I do a times x squared minus 2x, you get an a x squared minus 2ax. This b becomes a bx minus 2b, and the c is cx squared. And then it would all still be over x squared times by an x minus 2. And then we want that to be equal to our 4x squared minus 14x plus 8 all over an x squared times an x minus 2. So now we can group together like terms. So anything that has an x squared, you're going to group together. Anything that has an x, you'll group together. Anything that doesn't have any of those, you'll group together. And because the denominators here are equal, you can kind of ignore them from this point on up until you plug them back into your original equation. And so you have an a x squared and a cx squared is going to have to equal 4x squared. And you have a negative 2ax plus bx going to have to equal negative 14x. And your negative 2b going to have to equal 8. And that comes from just grouping together those like terms. Okay. And now we can kind of eliminate. So in this first equation, you see there's a bunch of x squareds. So those can all cancel out, and you just get an a plus c equals 4. This second equation becomes a negative 2a plus b equals negative 14. And that third equation is negative 2b equals 8. And you can solve from there. And so luckily these equations they give you aren't too bad. You don't need to really like put in a matrix or anything, because we can easily solve for what b is, because negative 2b equals 8. So therefore b equals negative 4. If you plug in negative 4 into that equation, that is your second equation there of negative 2a plus b equals negative 14. Negative 2a minus 4 is negative 14. Negative 2a equals negative 10, so a equals 5. Okay. And then you can plug a into that first equation, which is a plus c, so 5 plus c equals 4. So c equals negative 1. So then to finish it all off, what you do is you take those values and then you plug it back into your original one. And so this A up here really is, A was 5, so you'd end up with a 5 over x. Your B right there, come on, give me, there we go. Your B was -4, so you'd end up with a -4 over x squared. And your C, the only reason I'm erasing these is because I'm out of space. No. C is -1. So your full answer, what you would do is you would write -5x plus 5 plus all of that. So it'd end up looking like -5x plus 5 plus 5 over x plus a -4 over x squared plus -1 over x minus 2. And that's what you would plug in for your answer. There's a lot of steps to it, but yes.
Does it matter what coefficient we put on top of
No.
the, like, factor?
No. So like you could do the a over x minus 2 and then like b over x squared, c over x. It doesn't matter because when you put it back into your whatever you did originally, it'll work out. Because like in my notes, originally what I did was a over x squared plus b over x plus c over x minus 2, which isn't what I did here.
Yeah.
And you get the same answer. Yep. Okay. Well, that's everything. So good luck on your finals.
Thank you so much.